by summing up over the density of coils, the number of coils at each position. And this thing here is correct. It will give me the field along the axis of a solenoid, inside the solenoid and outside the solenoid, right, of a finite length. So this is good, right? For an infinite solenoid, so if we let L go to infinity, I have no idea, I have forgotten what the notation is. I'm going to write it like that. For L going to infinity, then this becomes 4 pi n I over c, the speed of light. Now, that's the magnetic field that we calculate from Biot-Savart on the axis of the solenoid for an infinite solenoid. But wait, there's something better that we can do here. So let's take a look at something better. But I'll write this down. This is what we calculated. The solenoid, the infinite solenoid, what we calculated on the axis is 4 pi n I over c. Okay. Now I'm going to take a brief vector calculus interlude. And we're going to come up with another way to calculate that magnetic field. So here's what we know from our relativity interlude. That the curl of the magnetic field is 4 pi over c j. And we also know that the divergence of the magnetic field is equal to 0. So what I'm going to do is take this curl and integrate it over a surface. So I'm going to take some surface, this is an arbitrary surface, and I'm going to perform the flux integral of that curl. Right? Not the flux of the magnetic field, but the flux of the curl. And that's the integral over the surface of 4 pi over c j dA. Right-hand side, we're going to leave the way it is. The right-hand side, if you read it, is the current enclosed by a path that surrounds the surface. But this is a surface integral here right now. And that's the total current that goes through that surface. All right? But on the left-hand side, I can now use Stokes' theorem. And that tells me that the integral around a closed path, B dot dl, let's say, that's just to indicate it's a line integral around the path, is the integral over the surface enclosed by that path of curl of that vector field. I may have lost a constant there, but it's not really important. We'll make sure the constant comes out in the end. But I don't think so. That's okay. It doesn't have to be the magnetic field. It's of any vector field. Right? Which means that I can rewrite this thing here on the left-hand side as the integral around the path, d dot dl, is equal to 4 pi over c, the integral over the surface enclosed by the path of j dot dA. the current enclosed. Yes.
But isn't it possible to say that the original left-hand side is 0 because it's the divergence of a curl? Or am I getting my identity?
How is it a divergence?
I'm not diverging anything there.
Oh no, because
If I took the divergence,
that's a regular dot product, not a
that's
Yeah.
just a dot product with the surface. It's the flux.
Okay.
It's the flux of the curl through the surface.
I messed up.
It's just flux. Okay? And that just comes from this. We integrated both sides over an area, and then we recognized that the curl dotted into the area surface is going to give me the path integral. This here is Ampere's law. So that's usually the first thing you learn in physics too. But I consider that it comes from Biot-Savart. Okay, so let's leave this one up. Where shall I put it? I'll move it over here. And then we'll employ it for a couple of calculations. Over the surface enclosed. Now that path integral is only easy when the magnetic field is constant over the path, or the magnetic field is 0. Or rather, the dot product of the magnetic field with the path that we're going to take is 0. It's only if it's constant or if it's 0 that it works. So let's take a look at our long wire. Actually, now it's got to be an infinite wire. I've got a current, and I want to calculate the magnetic field at some distance r from the current. And I can argue that the magnetic field is going to be of constant magnitude over the over a surface that is circular and has the current as its axis, right? Oh, let me do the right-hand side here. Okay, now I come back here. My magnetic field from the cross product that I would use for Biot-Savart tells me that the magnetic field for current traveling in that direction goes around in a circle. The magnetic field is independent of distance from the center. Again, I can get that from Biot-Savart without actually doing the integral. I can look at the form of the equation and realize that the magnetic field is constant in magnitude around that loop centered here, right? And so that means that if I take a path that's parallel to the magnetic field at every single point, the dot product goes away. Integral B dl. The magnetic field is constant in magnitude over that path, so it's B dl, which is V times 2 pi r is equal to 4 pi over c current enclosed. And so let's hope that this is actually going to work out. Right? It gives me 2 pi over rc. Yes. So Ampere's law gives us this conclusion relatively quickly, right? But if I had a finite wire here, it would be horrible. Ampere's law would not allow me to assume that the magnetic field is constant along this path. Because if I have a finite wire here, then I've got some wire that heads off in this direction. And I can choose this direction so that I can make the contribution of this wire to that point 0, but I can't make it 0 over here because this wire is not aligned with that point there. So my magnetic field is not constant. So for a finite wire, can't use Ampere's law. Only for an infinite wire. But when you can use it, boy, it really makes the problem a lot easier. So the answer is the same, and it's exact. So over there, we did the Biot-Savart integral, and we had this term that we threw out because we said that we got a really, really big constant, or nearly constant, right? We had to approximate. Over here, there was no approximation here, other than the need to make the statement that the field, that the wire is infinitely long, so that the field on this side is the same as the field on that side. Okay? You're looking troubled, Ryan. I don't know. No? Okay. So that's a long wire. How about, yeah, I like this one, a sheet of current. Oh, I should have erased Ampere's law. Equals, what were my units again? 4 pi over c, or?
Yeah, 4 pi over c.
Yeah, good.
U is
4
equal
pi over c integral j dot dA through the surface, right? What I'm going to do now is calculate, I shouldn't have put an end on this, right? The magnetic field due to current flowing everywhere at uniform density into a sheet, right? So once again, I can say, well, this thing's going to be very thin. I'm going to do the integral of j. No, actually, that's not important. Let's think about that. Yeah. I'm doing the integral of j through some surface, for example, like this. So that would be my cross-sectional area. And that's going to depend upon the thickness of the wire if I have j. I'm going to do the thickness integral. I just say, well, it's very thin. But if I do the thickness integral, then I'm going to end up with a, I'm trying to figure out what constant I should use. And I'm probably wrong in this choice, but I'm going to call it sigma current. All right? That's the current per unit length in a cross section across here. Maybe I should call it lambda current. Lambda. Lambda current. Okay? So I've got current density going in here, and lambda current is equal to J times D, where D is the thickness. Okay? But I'm just going to write it as lambda current there. So I just did part of my integral over here. And my J, I'm going to select a surface which is perpendicular to the current flow. All right? So that's going to make my dot product on the right-hand side, just 1. And this is going to be equal to then lambda d x. X is that direction there. Which is just 4 pi over c lambda. Let's take this thing here to be of length L. L. Okay? On the other side, then I want to calculate what the magnetic, the path integral of the magnetic field is. What I'm going to do is construct this surface here. Let me redraw it. There's my sheet of current going in. I'm going to construct an Amperian surface loop area, the path loop here, right? Such that the distance of the loop from the wire, from the sheet on this side is the same as the distance from that side. Now, Biot-Savart is going to tell us that the magnetic field up here is going to, if I have my current into the board, right, is going to be pointing that way. And the argument can always be made that if I have a little element of current over here, then I look at how that contributes to the field at this point. I'll have another bit of current over here on this side that's going to contribute. The z-axes are going to cancel out. And so any point for this infinite chain, any point the z-axis fields are going to cancel away. All right? So I'm okay with that. I know that down on the bottom is going to look like that. And there's no reason, based upon law of Biot-Savart, that the field will be different in magnitude here than it is there. All right? So I've got some field at some distance. Let's just call that the z distance. And over here, field at z. Those two fields are equal and opposite. All right? Now, I can always make, because this is an infinite sheet, I can make the ratio of this side to that side really, really big. And furthermore, I could have made the argument here that the field always points that way. Oops, wrong way. Here, here. Here. So two arguments. One is that I can make the ratio really, really big. And two is that for an infinite sheet at least, the field is parallel to the surface of the sheet. Okay? That means that the dot product over these paths on the ends is going to be 0. And so this left-hand side over here is going to be equal to 2L, that's the distance there and back, times the magnetic field at that distance R, equals 4 pi over C lambda L. L goes out, and I end up with the magnetic field at a distance R from the surface is 2 pi lambda over C. R doesn't appear here. For an infinite sheet of current, the magnetic field above or below the infinite sheet of current is independent of the distance from the sheet. Okay, so that gives us the field due to a sheet. Sheet is 2 pi lambda over C, and it's going to be parallel to the sheet, perpendicular to the current. So I won't put the direction up here. You have to figure that out. And now, one more. Should not have erased that, once again. And that's the solenoid.
Are you having fun with that?
What?
Drawing.
That's my solenoid. Actually, we had a group in XFIS who made a solenoid, and it looked just about like that at the time they were done. All right. So what are we going to argue here? Once again, I'll start with Ampere's law. And this time also, I'm going to choose a little box that goes like so. All right? But I can't make the argument that the magnetic field is the same above as below. Right? But what I will do is take, actually I think what I'm going to do is argue that I have a finite solenoid here. It's not infinitely long, so I won't consider that yet. But I will consider the point at the middle along this axis of the solenoid. So my magnetic field from this solenoid is going to pass along here, it's going to come out, it's going to go around, and the fields have got to come back upon themselves because the divergence of B is 0. So my magnetic field does that. And right away we can make some sort of argument that the field outside must be small compared to the inside field, Because for every line of field that goes this way, I'm going to get another line of field outside. And the field outside, it can spread out over a lot of space, and the field inside's got to be confined. So this is going to be a high field, and that's going to be low field. But we can do better than that, right? I can look at this, and I can say, well, if I get really, really far away from this finite solenoid, the magnetic field, Biot-Savart, tells me the magnetic field has got to drop as 1 over r cubed, I think it is, right? So magnetic field is going to decrease. So I can make this box that I draw here really, really big. Short, but very, very, the other end is very far away. And I can argue based upon symmetry, looking at the field lines that come like so. I might have a field line that goes in like that, but then I'll have a field line that goes out like that. They're going to be symmetric. The angle that goes in at will be equal to the angle that goes out at, as long as I've chosen the central axis of the solenoid. Okay. So that means that the path integral along this side and that side are going to cancel one another out. It's 0. And the path integral really, really, really far away at this finite length here is going to be 0. It's going to go to 0. Get far enough away, it drops off as 1 over r cubed, so I'm fine. So I've only got this bit here that I've got to worry about, okay? And that bit there gives me then d dl, so let's call that little thing that region that I just looked there, at length L. So B times L inside the solenoid is equal to 4 pi over C times the current density. The current density is equal to the current in each wire turn of the solenoid times the number of turns of wire per unit length. So actually, I'll just leave it like that. That's the number density of wires. And there. That's the number density of wires, but then how many wires actually go through here is going to be n times L. So the total current is the current per wire times the number of wires in this region. Okay? L goes out, and I'm left with the magnetic field at the center of the solenoid. Right? That doesn't depend upon where I drew this this Amperian loop here. Now, my argument just now just went for the magnetic field at the very center of the solenoid, right? And yeah, I'll just leave that as it is, right at the center of the central axis of the solenoid. That's what it looks like, right? And it's independent of position because of, you just look at the integral, and it's got to be independent of position. If I make the solenoid infinite in length, then that means that no matter where I am, I'm at the center of the solenoid. And so that applies no matter where I am inside of an infinite solenoid. Right? And I hope that agrees with what we deduced over there from the law of Biot-Savart. But that calculation that we did was just along the center axis, because that was the only one that was easy enough for us to do the integral on. Right? Whereas this one was based upon symmetry arguments. We had to have symmetry in order to be able to do this, and Ampere's law, which was deduced from Biot-Savart. Okay. Example. Okay. Actually, yeah, I'm going to save discussions of vector and scalar potentials until next time around. Josh.
What was n again?
The number of turns in the solenoid per unit length.
Thank you.
Okay, I have, as I think Alex realized at the beginning of this lecture, posted the homework that's due for when you come back. And there will be a quiz on relativity as it relates to electromagnetic fields. So you can expect that there will be a quiz on doing a Lorentz transformation on a field on Monday,
15.
when you come back.
And the homework is due Thursday, we come back.
Yes.
On field 10 first.